All right, you're welcome again. Today, we are still considering Laplace transform. Let's see what we have today. Let's take a look at the Laplace transform of the form e raised to the power of at f of t. All right, in our previous videos, in one of them, we have treated what we called first translation or shifting property, where you have e raised to the power of at f of t. All right, so but in this video we are going to build on that foundation to establish more principles. Okay, now look at this. Let's visit the first translation property a bit. We are going to use it for something. The first translation property states that if the Laplace transform of f of t is given as f of s, then the Laplace transform of e raised to the power of at f of t is going to give you f of s minus a. This is what the first translation or shifting property. Now, but what we are going to talk about today in this video is this. When f of t takes different form, how does it look like? When f of t takes what? Different form, how does it look like? Now, for instance, number one, when f of t is t raised to the power of n, or when f of t appears in this form, t raised to the power of n, how does it look like? That means we're going to say the Laplace transform of e raised to the power of at, t raised to the power of n. Please, this video is very important. Why it's very important is because it will help you when you will be treating inverse of a Laplace transform. Please, this is very important. Pay attention to this. Now, we are talking about the Laplace transform of e raised to the power of at f of t, where f of t takes any form or comes in different form. How does it work? Okay, how does it work? Now let's go. We say the first one, when f of t takes the form t raised to the power of n, when it comes in the form of t raised to the power of n, how does it work? Look at this. That means we say the Laplace transform of e raised to the power of at multiplied by t raised to the power of n. Okay, how does it work? First of all, we split this into two. When you have t raised to the power of n, let's first of all find the Laplace transform of t raised to the power of n. Good. Now, when we say the Laplace transform of t raised to the power of n, what does it give you? It's going to give you n factorial all over s raised to the power of n plus 1. I hope this is clear, right? Good. We have treated this in a separate video where we prove this property, or where we prove this elementary function. Please watch a video on that. It's very important. We have proved this. Watch it if you don't know how the Laplace transform of t raised to the power of n is equal to n factorial all over s raised to the power of n plus 1. Please try and watch the video. All right? Good. Now let's go. The first one, we first of all find the Laplace transform of t raised to the power of n. And when we do so, we have that he is giving us n factorial all over s raised to the power of n plus 1. Okay, good. Now, what of when you add or when you multiply this tn by e raised to the power of at? That is to say, when you say the Laplace transform of e raised to the power of at multiplied by t raised to the power of n, how does it work? How will it come? Now, please pay attention. From the first translation property, look at this. We say when you say the Laplace transform of f of t, it gives you f of s, right? And then when it is the Laplace transform of e raised to the power of at f of t, it gives you f of s minus a. Please look at this very well. It's telling you that when you have a function multiplied by e raised to the power of a, what is it going to give you? When you find the Laplace transform of the function f of t, okay, anywhere you see s, replace it with s minus a. Hello. Anywhere you see s, once you have found the Laplace transform of f of t, anywhere s appears, replace it with what? S minus a. If it is e raised to the power of at, a is a constant. It can assume any value. All right, good. Now look at this. Look at this. In this one we are solving now, we first of all find the Laplace transform of t raised to the power of n, and we say that it is n factorial all over s raised to the power of n plus 1, right? Good. Now, what if when you have this function multiplied by e raised to the power of at, what is it going to give you? We say anywhere we see s, we replace it with what? S minus a. So in this case now we have n factorial all over s raised to the power of n plus a. So in place of this s now, we write what? S minus a raised to the power of n plus 1. There is a condition given that s is greater than a. Hello. Now, maybe you did not understand this. Let's take an example. Look at this. This one says, find the Laplace transform of 2t raised to the power of 4 e raised to the power of 3t. Hello. We are to find the Laplace transform of 2t raised to the power of 4 multiplied by e raised to the power of 3t. Okay, good. Look at this. First of all, let's treat the linearity property. There's a constant here. We take it behind. When we take it behind, we're going to have 2. The Laplace transform of t raised to the power of 4 e raised to the power of 3t, right? Good. Now look at this. First of all, let's treat the Laplace transform of t raised to the power of 4. When we treat this one, what is it going to give us? Recall, it's going to give us what? 4 factorial all over s raised to the power of 4 plus 1. When you say 4 plus 1, it's going to give us what? 5. So that means the Laplace transform of t raised to the power of 4 is giving us what? 4 factorial all over s raised to the power of 5. Is that true? Yes. Now look at this. In this property we just treated now, we say when you have a function multiplied by e raised to the power of 8t. But in this case now we have e raised to the power of 3t. That is to say that our a is equal to 3. Hello. That is to say that our a is equal to what? 3. So anywhere we see s, we replace it with s minus 3 in place of s minus a. Hello. Look at this. Look at this. We have 2. The Laplace transform of t raised to the power of 4 multiplied by e raised to the power of 3t is equal to, we have 2 first. All right. Open bracket. Now, the Laplace transform of t raised to the power of 4 is giving us 4 factorial all over s raised to the power of 5. Right? Good. Now, because this t raised to the power of 4 is being multiplied by e raised to the power of 3t, so anywhere we see s, we replace it with what? S minus 3. Hello. So in this case, we are going to have 2 open bracket 4 factorial all over s minus 3 close the bracket raised to the power of 5. Okay. And I'm very sure you know what to do the rest. You can simplify. So 4 factorial simply means 4 times 3 times 2 times 1, right? Good. So when you say 4 times 3 times 2 times 1 multiplied by 2, is going to give you what? 48. So here we have 48 all over s minus 3 raised to the power of 5. Hello. Please, I hope you understand this, right? Good. Now let's take another one. We are talking about the Laplace transform of e raised to the power of 80 f of t, where f of t takes different form, right? We have taken the first one. We assume that f of t takes the form of t raised to the power of n, and we are able to take an example, right? Good. Now the second one, let's assume that f of t takes the form of sine omega t. Now, this omega, is a constant. It can be 80, it can be anything. This omega is a constant. You can assume any value, right? Good. Now let's go. That means we have the Laplace transform of e raised to the power of at sine omega t. Okay, now let's go. First of all, let's find the Laplace transform of sine omega t. The Laplace transform of sine omega t is going to give us omega all over sine squared plus omega squared. Hello, I hope you know this, right? We have proved this in our previous video. Please try and watch that. Okay, now let's go. Now this sine omega t is being multiplied by e raised to the power of at. How is it going to look like? That means in this Laplace transform of sine omega t, anywhere we see s, we replace it with s minus a, because it's being multiplied by e raised to the power of at. Hello, good. That means we have the Laplace transform of e raised to the power of at sine omega t is going to give us omega all over s minus a squared plus omega squared, given that s is greater than a. Okay, now let's go. Let me take an example. Let's take an example to explain this further, right? Good. Now let's see. We are to find the Laplace transform of e raised to the power of minus 2t sine 3t. Hello, we are asked to find the Laplace transform of e raised to the power of minus 2t sine 3t. How is it going to look like? Now let's go. First of all, let's find the Laplace transform of sine 3t. Okay, so the Laplace transform of sine 3t is going to give us 3 all over s squared plus 9. I hope you know this, right? Good. Now let's go. In this case now, we have e raised to the power of at multiplied by f of t, right? Good. So that means in this sine 3t now, anywhere we see s, we replace it with what? S minus a. Okay? But in this case now, you see that our a is what? Is minus 2. So that means we're going to say s minus open bracket minus 2. So that means we're going to say that the Laplace transform of e raised to the power of minus 2t sine 3t is going to give us 3 all over s minus open bracket minus 2 all the bracket squared plus 9. Okay, when you open the inner bracket, it's going to give us minus will give us plus. So we have s plus 2 in bracket squared plus 9. All right, good. Now this s plus 2 in bracket squared is telling you open it into 2, right? That means we're going to have 3 all over s plus 2 in bracket times s plus 2 in bracket plus 9. Okay, it's still the same thing, right? Good. Now when you multiply these two together, it's going to give us 3 all over. We have s times s will give us s squared, s times 2 will give us 2s, then the next one 2 times s will give us 2s, and then 2 times 2 will give us 4, right? When you combine these together, we have s squared plus 4s plus 4 plus 9. Is that clear? Yes. Good. In this case now, we have 3 all over s squared plus 4s plus 13. So therefore, the Laplace transform of e raised to the power of minus 2t sine 3t, it gives us what? 3 all over s squared plus 4s plus 13. I told you earlier, this form is very important when you are solving inverse of a Laplace transform. Okay, good. Now let's go. The third form now. Let's assume that our function f of t takes the form of Cosh omega t. Cosh omega t. That means we are going to say the Laplace transform of e raised to the power of at Cosh omega t. How is it going to be? First of all, we find the Laplace transform of Cosh omega t. So the Laplace transform of Cosh omega t is going to give us s all over s squared minus omega squared. All right, it's going to give us s all over s squared minus omega squared. All right, good. Now, when you say the Laplace transform of e raised to the power of at multiplied by Cosh omega t, how is it going to be? First of all, you have found the Laplace transform of Cosh omega t. So in this Laplace transform of Cosh omega t, anywhere you see s, you replace it with what? S minus a. All right, good. In this case now, in our numerator we have s. It's going to give us s minus a. Good. And then in the denominator we have s squared minus omega squared. So in place of s, we write s minus a squared minus omega squared. Is this clear? Good. Now let's take an example also to explain this. When you have the Laplace transform of 3e theta, 3e raised to the power of theta, Cosh 4 theta, we are asked to find the Laplace transform of 3e raised to the power of theta, Cosh 4 theta. How is it going to be? First of all, applying the linearity property, we have 3 here, right? It's a constant, we take it behind. So when we take it behind, we're going to have the Laplace transform of e raised to the power of theta, Cosh 4 theta. Okay, what is going to give us? Now let's go. First of all, let's take the Laplace transform of Cosh 4 theta. When you say the Laplace transform of Cosh 4 theta is going to give us s all over s squared minus 16. Hello. I hope you know this, right? Now let's go. We have taken the Laplace transform of Cosh 4 theta, right? Good. Now let's go in details now, or in full. Well, we have 3, the Laplace transform of e raised to the power of theta, Cosh 4 theta. What is going to give us? We have 3, right? Good. So now, in this Laplace transform of Cosh 4 theta, anywhere we see s, we replace it with what? S minus a. And then in this e raised to the power of theta, our a is what? Is 1. So that means we're going to replace with s minus 1. So here we have 3, open bracket. In our numerator we have s. We have s minus a, right? So, and our a is 1. That means we have s minus 1. In the denominator we have s squared. In place of s, we replace with s minus a, but in this case our a is 1. So we say s minus 1 in bracket squared minus 16. All right, good. Now the 3 outside, multiply the numerator. We're going to have 3, open bracket, s minus 1, close the bracket, all over. In the denominator, we have s minus 1 in bracket squared. You open it into 2 places. When you multiply the bracket, the 2 content in the bracket, it's going to give you s squared minus 2s plus 1. Then we have minus 16. So when you simplify, it's going to give you 3, open bracket, s minus 1 in bracket, all over s squared minus 2s minus 15. Hello. So the Laplace transform of 3 e raised to the power of theta, Cosh 4 theta, gives us 3, open bracket, s minus 1 all over s squared minus 2s minus 15. All right. Yes. I've taken some forms, and I'm very sure that with this example, you can take the rest of the forms. Now, take a look at this table. I want you to prove the rest. It's very simple. The same way we did the previous ones, you can prove the rest. Look at this table. The Laplace transform of e raised to the power of at, where t is n. We prove this, right? Good. And then the second one, sine omega t. And then the third one, cos omega t. The next one, we say psi omega t. And then we have Cosh omega t. These are what it will give you. Please, I want you to try them, work on them, and then share our videos. Please, if you are new to our YouTube channel, please like, share, subscribe, and stay blessed. See you some other time.